to finish up the section that we were talking about in our last lesson, Introduction to Functions, we're going to look at piecewise defined functions. This is something that we started looking at a couple of lessons ago, but it was a little out of context, and it was among a lot of other things that were also new. So we're going to step back for a second and think closely just about functions that look like this. We've got the function equals this part when x is negative and this part when x is positive. So over here, these are the constraints on the domain. This tells you when you're looking at each type of function here. So in other words, when I have a negative x, I'm going to plug in that x into this. When I have a positive x, I'm going to plug that x into this expression. Together, I will get all of the different values of y, or f of x. Remember that this notation means function of x. So I plug in a value of x into the function, and I get out the value of f of x. Okay, so here's an example. We've got this function here, and we want to evaluate it for f of -1. We also want to evaluate it for f of 0. And finally, we want to evaluate it for f of 1. Okay, so I am just going to create a chart that helps me organize my input values and my output values. So my input is my x. The function that I'm using is going to go in this middle column here, and then my output is the last column. So I'm going to say -1, 0, and 1 are my inputs. Now what I have to do is look at I'm looking at this input value, this -1, I see that -1 is less than 0, so that means it is in this constraint, it's in this category. So I'm going to use this expression to evaluate. So I'm going to have -1 squared plus 1 here. -1 squared plus 1 is 2. So when I plug in -1 into my function, I get out the value 2. I'm going to do the same thing for 0. But now 0 is included in this constraint here. X is greater than or equal to 0. So I'm going to plug in to this point. So I'm going to have 0 minus 1, which is equal to -1. My last number is 1. I'm going to plug it in. 1 is greater than 0, so I'm going to plug it in here. So I'm going to get 1 minus 1, which gives me a 0. In other words, when I plug in -1 into my function, I get 2. When I plug 0 into my function, I get -1. And when I plug 1 into my function, I get 0. Now we're going to talk a little bit about domain. We've talked about it in class before. We know that it's the numbers that we plug into a function. Most of the time it's denoted by x. We've also been talking about domain as our names. We were put into the sorting hat, and then the output is the houses that we were sorted into. So let's look at domain in these 4 different situations here. We're going to look at a function when it's given to us as an ordered pair, as a function with a variable in the denominator, as a formula for something specific, and with a square root. Now, one of the things that I want to say is that in any given situation, we're thinking about where does the domain exist? So on a graph, where does the actual line exist? And visually in a function, where does it make sense? What numbers make sense to plug into this function? We'll look at each of these individually. First, let's look at A. For something like this, which is what we've looked at in class already, we're just going to pull out the x values for each of these points, and that's going to be our domain. So we'll write this as our domain is, let's see, we've got a -3, -1, 0, 2, and 4. So these numbers represent the domain of this function. Now let's look at a function like this, where we have a variable in the denominator. Okay, when we've got a variable in the denominator, or just in general, we're thinking of when would this function not exist, or when does it not follow the same rules as normal. So we know that anytime we divide by 0, that is breaking all of the rules. We've called it undefined slope, or a line with undefined slope. Here, this function is going to do something very funky when we divide by 0. In other words, we want to exclude the value that makes this denominator 0 from our domain. That way the function can continue to do what it needs to do. So in order to do this, I'm going to say that 0 is the troublemaker. Okay, if my denominator is equal to 0. So I'm going to say 0, when does my denominator equal 0? I'm going to solve this equation to find what x is. So we see that when we plug in a -5 for x, then we get a denominator of 0. So our domain then is going to be all real numbers except for -5. There are a couple ways that we can write that. Okay, so the way that we can write this is we've got a domain such that x is all real numbers except 5. This is not equal to -5. Or we can use interval notation here, where we say that the domain is from -∞ to -5, union, or also -5 to +∞. So either of these describe the domain. Now we're going to look at when we have a formula for a specific situation. So here we're talking about the volume of a sphere. Volume is a measurement in three-dimensional space. So negative, and it's dependent upon, I'm going to read this to you, let's see. We've got volume is 4/3 pi r squared. So volume is dependent upon this radius value here. And when you're measuring a sphere, it doesn't make sense to have negative measurements, right? And I can't be -3 feet tall. So for here, the numbers that I want to plug into R got to be greater than 0 in order for this formula to make sense situationally. So I don't have to do any calculations for this one. I just have to reason through and think that I want R to be bigger than 0. So this is, this is my domain here. My domain is all real numbers, R is all real numbers, greater than 0. Our final view is when we have a function that looks like this. We've got a square root. So now I'm thinking, okay, I know what the square root of 4 is, 2, 25 is 5, but what about square root of -4? The square root of -4. Well, if I've studied complex numbers, then I know that this is going to be plus or minus 2i. But if I haven't, then all I know so far is that we've got square root of -4, which is just something that I've never been able to do before. Also, if I know that I've studied imaginary numbers, I know that it's very complicated to put this on a graph. It's hard to make it appear. So when I'm looking at a function like this, I'm going to make sure that anything that's underneath the radical is positive. Okay? In other words, the function doesn't exist where this value is negative. So to set that up, I'm going to say I want 4 minus x squared to be greater than or equal to 0. And then I'm going to figure this out. In order to solve this, I need to remember a little bit of factoring. So factoring is when I break this binomial into two parts. I'm going to have 2 plus x and 2 minus x is greater than or equal to 0. So I've got, then I can break this down and say 2 plus x is greater than or equal to 0, and 2 minus x is greater than or equal to 0. And break these both down and see I've got x is greater than or equal to -2, and negative x is greater than or equal to -2, so x is less than or equal to 2. In other words, let's see, I'm going to grab, hold on. I'm going to say, I'm going to look at this constraint and that one. I've got -2 is less than or equal to x, and x is less than or equal to 2. So in other words, my domain is all of the numbers in between and including -2 to 2. So here we've got, let's just reiterate. When we've got a list of ordered pairs, our domain is just the x values. When we've got an equation or a function with a variable in the denominator, my domain is every real number except the numbers that make the denominator 0. So I set the denominator equal to 0, solve the equation, and I find the excluded numbers. When I've got a situation, sort of a real-life situation or a formula, I think to myself, what numbers make sense to plug in? So here I've got a measurement, a radius, and I have no volume at 0, so it really only makes sense to calculate volume when the radius is bigger than 0. And then finally, I've got a square root function where negative square roots, so a number, the whole expression underneath the radical, I want to be positive. So I pulled out that expression, set it greater than or equal to 0, and then I just had to remember a little bit of factoring, and then splitting it up to solve and figure out what the constraints on x are. So anything that makes that expression negative, I've excluded. So my domain is -2, including -2, all the way up and including +2.